All right. So, we have shown in the past that all representations of finite groups are completely reducible. This is Match-Key's theorem. And now our goal is to prove the uniqueness of that decomposition into irreducible representations. And to do this, what we're going to do is we're going to define finally a function. So for a representation phi, what we're going to do is we're going to define a function chi phi, which maps the underlying group to the complex numbers. And this thing will be called a character. So specifically, it's called the character of phi. And the way it's defined is chi phi of g is equal to the trace of phi g. So in this entire lecture today, we're going to take the matrix picture where the representation takes a group element to a matrix. We'll abandon the linear map picture for now. Okay, so the idea is that lots of information about this representation is somehow encoded in this character function, which is essentially just the trace operator. So maybe just a couple of remarks before I continue. So another way of writing this is the sum from I equals 1 to n, phi I of g. Right, remember we identified the components of the matrix phi g with ij. We called this phi ij of g. Okay, and notice that if phi has degree 1, then what's chi phi? Well, when it acts on g, this is the trace of phi g, but phi g itself is just a number, and so this is just phi g. So in this picture, the character is just the representation itself. So this kind of hints that the representation theory, well, maybe I shouldn't say that the character is an extension, but there is information encoded in the character function. Here's another piece of information that you can very easily see. So let phi be a representation of g. Then chi phi of the identity is equal to the degree of phi, which remember is the dimension of the underlying vector space, right? So phi is a representation. So okay, so maybe I shouldn't write v here because we're taking the matrix picture. So really I should write v equal to cn for some n. Okay, so what's the proof of this? Well, chi phi of 1 is the trace of phi 1 by definition. And since a representation is a homomorphism, it always sends the identity to the identity. So this gets sent to the identity matrix. And the trace of the identity matrix is the dimension of the underlying vector space, which is the degree of phi. So the degree of the representation is encoded in the character. That's good. There's other information encoded in it that we'll get to later. But first, I want to mention a nice property that we're going to use. If phi and rho are equivalent representations, then chi phi is equal to chi rho. So equivalent representations have the same characters. This is one of the reasons this is going to be incredibly useful. So here's the proof of that. So since phi is equivalent to rho, there is an isomorphism or a invertible matrix such that phi g is T rho G T inverse. So that's the definition of equivalent representations. It's for all G in the group. So first, recall that the trace has this nice property that the trace of AB is equal to the trace of BA. Well, then the character of phi applied to G is equal to the trace of phi G, which is the trace of T. Maybe I should add another step here. No, sorry, that's correct. T inverse T phi G. So I've added in the identity here. And then we use this property to write this as the trace of T phi G T inverse, which is the trace of rho G, and that's equal to chi rho of G. And so that implies that chi phi is equal to chi rho, because G is arbitrary. Okay, so equivalent representations have the same character. So we're also going to use this next result. Phi be a representation of G, then for all GH and G, we have chi phi of G is equal to chi phi of HG H inverse. So essentially what this says is that the character function is constant on every conjugacy class of the group. So if I have a group, let's call it G, and if I multiply on the left and the right, like so, then what I'm doing is I'm conjugating the group. And for let's see, maybe I should say, well, okay, maybe I'm going too far off here. The point is that conjugating will split the group into conjugacy classes, right? And these classes are disjoint from each other. And the character function is going to be constant on each of these conjugacy classes. So that notion of a conjugacy class can be used to give an equivalence relation. And so what you can say is that things that are connected by a conjugation have the same character, or the character acts on them the same at least. And that's exactly what we're saying here. Okay, so the point is this function is constant on conjugacy classes. And the proof is not hard. It's just a straightforward computation. So by definition, the character acting on HGH inverse is the trace of phi on HGH inverse. And this phi thing, remember, is a homomorphism. So we can use that property to write this as phi h, phi g, phi h inverse. And this is the trace of phi h inverse, phi h, phi g. By that property, trace AB equals trace BA. And we use that homomorphism property again to write this as trace of phi h inverse h, phi g. H inverse h is the identity, and a homomorphism maps the identity to the identity. So this is just going to be trace of phi g. Okay, and this is the character of phi applied to g. Okay, so again, the character function is constant on every conjugacy class. Okay. So a function f from g to the complex numbers, such as the character of a representation, is called a class function. If it's invariant under, well, if it acts the same under conjugation. Okay, so equivalently, this is just the condition that f is constant on conjugacy classes of g. So the space of class functions is denoted z of L of g. This L of g was what we called the group algebra. And if you've taken a little algebra, you'll know that this z symbol here is usually used to denote some kind of centralizer. And there's a reason, there's going to be a reason for that we'll get to later. But this is, again, the space of class functions. Okay, so I won't prove it, but this is indeed a subspace of the group algebra. So you could prove that that's a vector space. So here's a question. What is the dimension of the space of class functions? Well, if you denote by CL of G the set of conjugacy classes of G, and define for C a conjugacy class, you can define the function delta C from G to C by delta C of G is 1 if G is in the conjugacy class and 0 otherwise. So this is a pretty standard construction. And the idea is that this thing is, or the collection of all these things will form a basis. So proposition, the set B of all of these functions is a basis for the set of class functions. So a consequence of this is that the dimension of this space is equal to the order of the conjugacy class space. Or sorry, it's not a space; it's a set. So it's equal to the number of conjugates of classes.
Can I ask a question?
Sure.
So are you talking about the dimension as a linear space or just as a number of elements of a set?
As a linear space.
Okay, thank you.
Mm-hmm. Okay, so it's clear that delta C is a class function, just by definition, right? Because well, it maps from G to C, right? As in our definition, and it's definitely closed under conjugation because well, the definition only depends on the conjugacy class. Okay, so we have that. Now to finish the proof, let's let F be in the group algebra. Well, then we can write F as the sum over the conjugacy classes of F of C delta C. Okay. So why is this the case? Because, well, F of G is equal to F of C prime when G is in C prime. Because we're assuming that F is in the space of class functions. So this immediately establishes that B spans the space of class functions. Okay, so for linear independence, what we're going to do is we're going to verify that B, so the set of all these delta C functions is actually an orthogonal set of non-zero vectors. We're going to do that because, remember, orthogonality implies linear independence. So if C prime are conjugacy classes, then the inner product of delta C with delta C prime, I did not say what the inner product was on this space. This is a space that we proved was an inner product space earlier when I did I want to say linear algebra. And the inner product, well, let me write down exactly what it is here, and you'll see which one it is. I think I used it last time as well. So the inner product of F and G is the average over the elements of G of the first function evaluated at G times the complex conjugate of the second function. And in this case, what is this equal to? Well, this is equal to the order of C, so the number of elements in the conjugacy class C, over the number of elements in the group, if C is equal to C prime. So if C is equal to C prime, look, notice that we're plugging in the same group element here. We know that the conjugacy classes are disjoint from each other. And that means that if these conjugacy classes are the same, then both of these functions will be either 1 or 0. In the event that that G is in the conjugacy class, we get 1. How many times does that happen? Well, the number of elements in the conjugacy class is the number of times that happens. And this order of G here just comes from the order of G over here. Now, if the conjugacy classes are different, since we're plugging in the same element here, and the conjugacy classes are disjoint, that means that one of these will always be 0, and so we'll always get 0 here. And so this shows that B is a basis because we've shown that delta C and delta C prime are orthogonal, and that implies linear independence. So that implies that B is a basis. And as a consequence, since the order of B is equal to the number of conjugacy classes, that implies that the dimension of the space of class functions is equal to the order of, or the number of conjugacy classes. Okay, so that was a bunch of nice small results that we'll definitely use later on. Now let me give you a major result. So the next theorem shows that the irreducible characters. So the irreducible character is called irreducible if the representation that it's a character of is irreducible. So if I have a phi, which is an irreducible representation, then chi phi is called an irreducible character. So the next theorem shows that the irreducible characters form an orthonormal set of class functions. And we're going to use this to establish the uniqueness of the decomposition of a representation into irreducible constituents. And we're going to use it to compute exactly the number of equivalence classes of irreducible representations. Okay, so here's the theorem. So let phi and rho be irreducible representations of some group G. Then the inner product of chi phi with chi rho, so the inner product of the characters, is 1 if phi is equivalent to rho, and 0 otherwise. My not equivalent symbol looks like a chi. I apologize. Okay, so this tells us our conclusion is the irreducible characters form an orthonormal set. Okay, here's the proof. So recall that every representation of a finite group is equivalent to a unitary one. We proved this using Weil's unitary trick, or what Steinberg calls the averaging trick, where you just redefine the inner product so that all of your operators are now unitary with respect to that inner product, the new one. So we can safely assume that phi and rho are unitary. So remember, equivalent representations have the same character. So that's the reason that we're using this property. Well, then the inner product of chi phi with chi rho, by definition, is 1 over the order of G, sum over G and G, chi phi of G, chi rho of G complex conjugate. And this is equal to so by definition, the sum from I equals 1 to n of phi I of G. So this n here is the degree of phi, and I'm going to use m for the degree of rho. go. And now I'm going to pull these two sums out to the left. So we'll get sum from I equals 1 to n. No issues here because we assume our group is finite. Right? We assume the group is finite, so no issues with convergence here. We can always pull these things away from each other. Phi I of G, rho J of G, complex conjugate. And this, well, this is the sum from I equals 1 to n, sum from J equals 1 to m of the inner product of phi I with rho J. And this is where Schur's orthogonality relations from, I believe, last time come into play. So I'll remind you what they say. They're a little tough to remember, maybe. So they tell us that phi I rho J equal to 0 if these representations are not equivalent to each other. It says a little more, but we don't need it. The point is that if the representations are not equivalent, then this inner product will be 0. So that's one of Schur's orthogonality relations. So chi phi, chi rho is equal to 0 if phi is not equivalent to rho. I'm stretching this out so it looks less like a chi. Okay. So on the other hand, so that establishes this part here. So on the other hand, if phi is equivalent to rho, then chi phi is equal to chi rho. So we proved that earlier. Well, then that means that chi phi chi rho is just chi phi inner product with itself, which is the sum, I equals 1 to n, sum from j equals 1 to n of phi I, phi j, right? I'm just pulling this from here. And we again use Schur's orthogonality relations. So when the representations are the same, the orthogonality relations say that phi I, phi j is equal to 1 over n, where I equal to j, and 0 otherwise. So remember that n is the degree of phi. And we use this, and this implies that chi phi, inner product with chi rho, and the event that these are the same, or equivalent at least, this is equal to the sum from I equals 1 to n of phi I, phi I, because all other terms are 0. And this is the sum from I equals 1 to n of 1 over n, which is just 1. And that establishes the second part, or rather the first part. We did them out of order. And so that completes the proof. Okay. So we know now that the characters of the irreducible representations of a group form an orthonormal set. So that is a very nice property to have. And we'll use that again. But here's a nice corollary, just as an aside. Actually, is this? This would not be an aside. This is actually useful for our discussion. So here's a corollary. There are at most order of the set of conjugacy classes equivalence classes of irreducible representations of G. Okay. So maybe that isn't so clear. Let's prove it. So by the theorem, irreducible characters form a linearly independent set because, well, they're orthogonal, and orthogonality implies linear independence. Now, since the dimension of Z of L of G, so the dimension of the space of class functions, is equal to the order of CL of G as we proved, then the corollary follows. So again, the orthonormality given by the previous theorem implies that the irreducible characters form a linearly independent set in the space of class functions. And so the dimension of the space of class functions being equal to the set of conjugacy classes proves the corollary. Okay. So let's let phi1 through phi s be a complete set of irreducible representations of G up to equivalence. And we'll set di equal to the degree of phi I. Okay, so this will hold throughout the rest of the lecture. Definition. If I think I missed something in my notes here. What did I call it? I think rho. Okay. If rho is equivalent to phi 1, I'll explain this notation in a moment. Okay, so if rho is equivalent to a direct sum of m1 copies of phi 1, so this is phi 1 plus phi 1 plus phi 1, blah, 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 m1 times, direct sum all the way up to phi s and ms copies of phi s, then mi is called the multiplicity of phi I in rho. If mi is greater than 0, then we say that phi I is an irreducible constituent of rho. Okay, so a word of warning. So it's not clear yet that the multiplicity is well defined because we haven't shown that the decomposition of a representation into irreducible representations is unique, which is the whole point of today. So what would be nice is if we could compute the multiplicity directly from the character of rho, because the character of rho depends only on the equivalence classes of irreducible representations. So it would then follow that the multiplicity of phi I is the same no matter how we decompose rho. So, and I should also point out maybe just a quick remark. if rho is equivalent to phi 1, m1, blah 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 up to phi s plus ms, then the degree of rho is m1 d1 summed all the way up to ms ds. Okay, so let's just keep that in mind. So we're going to move on to proving this uniqueness of this decomposition. And I believe we just need one more lemma. Which isn't hard at all to prove. In fact, you might think it's obvious. Let phi be equal to rho direct sum with psi. Then chi phi is equal to chi rho plus chi psi. So the character of a direct sum is equal to the sum of the characters of the individual pieces. Proof. Well, chi rho plus chi psi apply to G. This is the trace of rho G plus the trace of psi G. And that's equal to the trace of, using capital T's, that's the trace of rho G plus psi G, using the linearity of the trace. And this is equal to the trace of rho plus psi G. So the easy way to see this is the matrix picture. Right, remember rho plus psi G as a matrix is just rho G psi G down the diagonal. So the trace is just the sum of these traces. And then this is equal to the trace of phi G, which is chi phi of G. And so that implies that chi phi is chi rho plus chi psi. So the character of a direct sum of representations is the sum of the characters. So the lemma implies that every character is an integral linear combination of irreducible characters, right? Because for any representation, I can decompose it into a direct sum of irreducible representations. So every character is a linear combination, or an integral linear combination specifically, of irreducible characters. Okay, so now let's use the orthonormality of irreducible characters to extract these coefficients. Let phi 1 through phi s, by coefficients I meant the constants mi. So in Steinberg, he writes them in front of the representation, which I didn't really like. It kind of just looks like you're multiplying a function by a constant number, but that's not what he means. So let phi 1 through phi s be a complete set. Okay, I've already said this, of irreps. Okay, I'll just say this again. Let phi 1 through phi s be a complete set of representations of the equivalence classes of irreducible representations. I should say a complete set of representatives, not representations. Let phi1 through phi s be a complete set of representatives of the equivalence classes of irreducible representations of G, and let rho be equivalent to, again, phi1 plus m1 through phi s ms times. So all the things we've been assuming already. Well, then mi is the inner product of chi rho with chi phi I. And consequently, the decomposition of rho into irreducible constituents is unique. And rho is determined up to equivalence class by its character. Okay, so this is the big theorem. Let's prove it. Actually, it's not hard. So by the lemma, phi rho is equal to m1 chi phi 1 summed up through ms chi phi s. Okay, so that's just exactly what our lemma is telling us. By the orthogonality relations that we proved earlier, we have chi rho, chi phi I is, well, it's m1 inner product chi phi 1 chi phi I. So I'm just using the linearity of the components of the inner product. Summed through, we're going to end on ms, chi phi s, chi phi I. Okay, and what is this? This is mi by our orthogonality relations for the character functions. So remember what they said was that the irreducible characters of a finite group form an orthonormal basis for the space of class functions. Okay, so the only inner product that survives here is the ith one, and the inner product is 1, because we have orthonormality, and so all that's left is mi, and that proves it. So again, what does this tell us? As a consequence, well, the decomposition of this representation rho into the irreducible constituents is unique, and rho is determined up to equivalence by its character. Okay, so in particular, here's an incredibly nice corollary. If you ever have a representation and you want to know, is it irreducible? Representation rho is irreducible if and only if the inner product of its character with itself is equal to 1. So let's go ahead and prove that. Okay, so we suppose rho is of this form again. I don't want to write it out again. Using the orthonormality of irreducible characters, we have that chi rho inner product with itself is just m1 squared sum through ms squared. All of the inner products become 0 except for when the constituents are the same index, and then their inner product becomes 1. Okay. And note that mi is greater than or equal to 0. Doesn't make sense to direct sum a negative number of things, or maybe it does. And I don't know the extension to the negative numbers. That happens a lot. But anyway, so chi rho is equal to 1 if and only if there exists a j between 1 and s such that mi is equal to 0 for I not equal to j, and mj is equal to 1. And that's just the same as saying that rho is irreducible. Right, because we broke rho down into a direct sum of the constituents. If all of these mi's are 0 except for one of them, which is equal to 1, well, then rho is just equivalent to a single irreducible representation. Right? And so rho is irreducible. And that completes the proof. Okay, so this is my probably favorite result that we've done so far. Is in the past, before I learned this character theory, I've struggled a little bit with proving that representations are irreducible. But what does it come down to? I mean, it's just computing the trace of the individually represented elements and summing up some stuff and checking that it's equal to 1. Right? So what I want to do is now let's see this theory work in action. So remember the group S3, which is the identity 1, 2, 1, 3, 2, 3, 1, 2, 3, and the 1, 3, 2 permutations. Define a representation by rho from S3 to GL2 of C, and we'll define it by rho 1, 2 is -1, -1, 0, 1, and rho 1, 2, 3 is -1, -1, 1, 0. So since 1, 2 and so since the swap 1, 2 and the 1, 2, 3 permutation generate S3, this actually defines the entire permutation or the entire representation. But let's just, to be extremely explicit, let's just write out what everything is. So rho 1, 3, 2, we get this one from the fact that this is rho 1, 2, 3, 1, 2, 3, which is rho 1, 2, 3, rho 1, 2, 3. And now we just multiply the matrices. Okay? And what do we get? Let's see, we get 0, 1, -1, -1. So I do the same thing for all the other elements. Well, the identity always gets sent to the identity because rho is a homomorphism. And I can write rho 2, 3 as rho 1, 2 times 1, 2, 3. And that will come out to 0, 1, 1, 0. And rho 1, 3 I can write as rho 1, 2, 1, 3, 2, which will come out to 1, 0, -1, -1. Okay, so let's see the theory in action here. What do we have to do? We need to compute the characters of these things. Chi rho of E, well, that's just the trace of this matrix, which is 2. Chi rho of 1, 2. So here's my 1, 2 matrix. -1 plus 1 is 0. Sorry for the smudge. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, chi rho of 2, 3 will also be 0, right? Where's 2, 3? It's right here. 0 plus 0 is 0. Chi rho of 1, 2, 3. Oh, I forgot my 1, 3. I'll do that one next. This one is -1. Chi rho of 1, 3 is going to be 0. And chi rho of 1, 3, 2 will be -1. So we didn't actually have to compute all of these individually because the character function is constant on conjugacy classes. So if you already know the conjugacy classes of the symmetric group, then you just have to compute it for one element and then assign that value to everything in the conjugacy class. Okay, but I just wanted to write it out to be extremely explicit. Okay, so then what we're trying to figure out is whether or not rho is irreducible. Well, we have that chi rho inner product with itself is 1 over the order of the group, which is 6, times 2 squared plus 0 squared plus 0 squared plus 0 squared plus -1 squared plus -1 squared. So these are the squares of the characters of each of the elements. Okay, and this comes out to exactly 1. And so that implies that rho is irreducible. Okay. So maybe I should say what happened in between here and here. So you can write chi rho as, remember, an integral sum, or an integral linear combination of the irreducible characters, right? And then you just inner product. Right? And so what's left is oh wait. No, sorry, this is just the definition of the inner product here. This is 1 over the order of the group, and you sum over chi rho of G complex conjugate. Yeah, sorry, that's my bad. Okay, so we currently know of 2 irreducible representations of S3. Okay, so the first one is the trivial representation, and it has degree 1. And now we know a second one, so I'll call it the previous representation of degree 2. Now, the order of S3 is 6, and we know that if if di, if this denotes the degree of the irreducible constituents, so I'm running out of ink here. Ooh. And okay, let's try this one. Well then, the sum over I of di squared is less than or equal to the order of not G, S3, which is equal to 6. So something we proved earlier. We currently have So the sum of the squares of these is 5, which is less than 6. So we do have room for one more irreducible representation if it exists. Any guesses? Let's see. You just send a permutation to its sign, which is 1 if sigma is even and 0 if sigma is odd. Okay, so I claim that this thing is irreducible. Well, this is obviously degree 1, right? We're mapping it to just C star. The dimension of the vector space is 1. So that means that chi rho is just equal to the representation itself. Yeah, I'll write it that way. Okay. So chi rho is equal to the sine function. So chi rho inner product with itself is 1/6. 1 squared. This comes from the identity. The sign of the 1-2 permutation. So the sign of all the transpositions is -1. There's 3 of those. And then the sign of the 2 3 cycles is 1. We add all those up and we get 1. And so that implies that rho is irreducible.
I think you made a slight typo when you defined your sine function of sigma.
Yes, thank you.
-1.
Yes, thank you very much. -1. In fact, it's correct in my notes. I don't know why I did that. Okay, so let's. But this is definitely all 3 irreducible representations, right? Because now we have the sum here is equal to 6. There's no more room. So let's arrange the characters of S3 into a table. So I'll call them chi1, chi2, and chi3. So this is the trivial one. Trivial. This is the degree 2 representation, and this is the sine representation. And above it, let's put our group elements. Two, 3. 1, 2, 3. And I'm missing 1, 3, 2. And we can write in the value of all these characters. So the trivial representation, just all the characters will be 1. Everything gets mapped to just the number 1. And then for the degree 2, we work those out. Those were 2, 0, 0, 0, -1, -1. And for the sine representation, we work those out as well. It'll be 1, -1, -1, -1, 1, 1. Okay, so remember the standard representation of S3? That was one we did. Well, that was a degree 3 representation, which sent identity, sorry, e to the identity, and maybe I'll just list like 1 or 2 of these. Phi 1, 2. The way we construct the matrix is we permute the rows according to the permutation. So row 1 gets swapped with row 2 in the identity matrix, and we get 0, 1, 0, 1, 0, 0, 0, 0, 1. And I'll do maybe a 3 cycle. Row 1, 2, 3. So the first one gets sent to the second one. The second row gets sent to the third row, and the third row gets sent to the first row. Okay, so this is called the standard representation of S3. There are 3 more things to write out, but I won't do that. And we can construct the character table here. So E, well, the trace of this is going to be 3. Trace of 1, 2 is going to be 1. And 1, 2, 1, 3, and 2, 3 will always be the same because they're in the same conjugacy class. And then 1, 2, 3, and 1, 3, 2 are also in the same conjugacy class. And their trace is 1, no, wrong one, 0. Okay, so we already know that this thing is reducible because it doesn't match the degree of any of the irreducible representations up here. What we could do though is we could square each of these, sum them up, and what you'll find is that when you divide it by the order of the group, you'll get 2 instead of 1. Right? So it's definitely reducible. And now the question is, how does phi decompose? Well, all we have to do to compute that is take the inner product chi5 with chi1, and that'll tell us how much of chi1 is present in the representation. And this is 1/6. So this is the trace. So this is chi-phi of E, which is 3 times chi1 of E, which is 1, plus chi-phi of 1, 2, which is 1, times chi1 of 1, 2, which is 1, and so on. So I'll just write the rest out. And what you get is 1. Now, chi-phi, chi2, what you'll find, so again, this would be 1/6. Chi-phi of the identity is 3. Chi2 of the identity is 2. Plus chi-phi of 1, 2 is 1. Chi2 of 1, 2 is 0. And I'll, again, list the rest out. And again, we get 1. And then chi-phi of chi3. And I'll just tell you what this one is. This one comes out to 0. And so what this tells us is that chi-phi is equal to chi1 plus, there's an error in my notes. This is chi1 plus chi2. And hence, since the irreducible representations are determined determined by their character, we see that phi is equivalent to the trivial representation plus that degree 2 representation, which I think we called rho. And so it's just as simple as that. I mean, it really doesn't get any simpler. Any questions?
I have like a very poorly worded question.
All right.
So you were talking about before we found, or before you showed the sign representation, you did that sum of di squared is equal to, or is bounded above by the norm of the group.
Yeah.
Can we always find the is that like always equality? Can we always find enough irreducible representations that it is actually equal to the size of the group?
I believe the answer is yes. I don't think we've gotten to it yet, but I think that's going to be in the next section, maybe.
Okay, cool.
Yeah, but I'm pretty sure the answer is yes. Okay. All right, so let's stop there.
So I guess algorithmically, you just look at how many ways you can kind of partition the size of the group into sum of squares or whatever. if you're like trying to look for the representations or something
Yeah,
like that.
yeah, that's a very useful calculation to have. Exactly. Yeah, exactly. Okay.